Hello again. Now in this lecture, we will talk about first law of thermodynamics. So before we go to reach the first law of thermodynamics, let's talk a few definitions, key terminologies. So we will talk about thermodynamic systems, and thermodynamic systems are objects that may have the potential to exchange energy with its surroundings. Another term is thermodynamic process, a process in which there are changes in the state of a thermodynamic system is called a thermodynamic process. So let's talk about a system. So let's say a system could be a container containing gas. So let's say this is my system, and anything outside the system is called surroundings, or we also call it environment, right? So couple of things we need to do. If I supply thermal energy, so let's say I supply thermal energy to the system, so let's say Q is the thermal energy supplied to the system, and there's work done by the system. So system does the work, and let's say work is done by the system. So when we supply energy to the system, or when or say let's say heat Q is positive when it enters the system, right? And same way, work and the system does the work on the environment, so work is positive when it is done by the system, right? Okay, so on the same system, this is, you can think of sign convention. So let's say this is my system. So heat is positive and enters the system. What happens to heat if it is leaving the system? Then Q is negative. So Q is negative when it leaves the system, right? So I'm using another color. And when work is done on this system, so work is done on this system, so this is W, let's say, and then W work is negative if it is done on this system. Okay, so this is sign convention we will use. Good. In this whole process, when heat is entered, and in this process, when Q heat is entered into the system or leaving the system, work done by the system or work done on the system, we all assume that all such changes occur slowly, with the result that the system is always in thermal equilibrium. So our system is always in. All right, in this lecture, we'll talk about heat and work. Let's take a system. So let's take, I'll consider our system of gas contained in a cylinder with a movable piston and on top of this piston you have some lead shot. The walls of the cylinder are insulated, so no thermal energy, no heat can enter or exit from this system. The cylinder is placed or sitting on a thermal reservoir, and with a temperature control knob, so temperature of the thermal reservoir can be increased or changed. So a thermal energy Q, heat energy Q, can enter into the system. And the W is the weight force, the force due to the weight of the lead shot and the piston. Okay, so suppose that we remove a few lead shots from the piston. So when we take out a few lead shot, that means the the force allowing the gas allowing the gas to push the piston upward. So since this piston is moving upward, there's a displacement. So the displacement, so this piston moves up. Let's say this is the displacement, and I just use as a vector displacement. This is displacement, with an upward force F, right? So work done by this force, let's call it dW. Work done by this force is force times our vector product, dot product of this and force and the displacement. And force is pressure per unit area. Pressure is force per unit area, so PA. Force is PA times ds times cosine of 0 degree, because force and displacement, they're parallel to each other, right? They're in the same direction. So I can say dW, a small element of small amount of work done, is P, and A is the area of the piston, and ds is the displacement. So I can say A times ds is nothing but the volume of that change in volume. So dW is P dV. So this is a differential change in the volume of the gas. And here we made an adjustment. Since ds is a small, we assume that F, the force, is constant. So when you have removed enough shot to allow the gas to change its volume from V initial volume to V final, the total work done, let's say W, is equal to work done in changing gas volume, in changing gas volume from initial volume Vi to final volume, let's say Vf. Then we can differentiate this small dW to V initial to V final. We can take the integral, and then that will be V initial, V final, and this will be P dV, right? So we got a definition of work is integral Vi to Vf P dV. All right. So if you want to determine the work done, we need to know how the pressure varies with volume for the actual process by which the system changes from state I to state F. So we need to know the whole equation there. Great. So what's the work done during volume change? So let's consider a PV diagram. So on this y-axis we have P, pressure, and on the x-axis we have volume. PV diagram for a system undergoing an expansion with varying pressure. So for the initial volume Vi, there's a pressure, corresponding pressure Pi. As the system volume changes from initial volume Vi to final volume Vf, the pressure reduces to final pressure Pf. So work done is equal to the area under the PV graph, and area under the PV diagram. So how much work is done? So if we integrate this area, the whole area, if I integrate the whole area, then so we know that work is equal to P dV, and then volume is V initial to V final, right? That's what we saw in the earlier. So P dV, this. And this work is, since its volume is larger, is expanding, this work done is positive, right? What happens if this was my initial volume and this was my final volume, and my volume changed this way? So after pressure Pi to Pf, volume changed, become smaller, it gets compressed, then work done will be negative, right? Then it will indicate a negative work, right? So the summary here that we need to remember is the work done is equal to the area under the curve under the PV diagram. So this is a very important fact to remember. All right, let's remove this.